So what we're looking at here is a big reactor here. And what ends up happening is we start off with some alkene and a water source that is coming out of a shower head that goes in through this reactor, goes through a distillation and another heteroisotropic distillation to give us products of an ether and an alcohol. And so let's just illustrate this a little bit, I guess. So, okay. For this reaction, we are starting with propene, which looks something like this. This is C3H6. And we are going to, from the shower head, we're going to have water coming out. And this produces our isopropanol. So this is our first reaction. This is what's happening in our first reaction. And what further ends up happening in this trickle bed reactor here is we have some polystyrene beads that are treated with a sulfuric acid catalyst. And what this catalyst allows us to do, it allows this product to undergo Williamson ether synthesis. So we have now our isopropanol, two of these to be exact, and it's going to, using that catalyst, it's going to undergo Williamson ether synthesis, and we are going to have our diisopropyl ether. And as a byproduct, we have water. So this is our second reaction that we're looking at. Make sure you can see that. This is our reaction 2. So if we redraw this a little bit, just simplify it down a little bit, we have a box. And this box is our reactor here. So it's going to be all of this. It's going to be all this stuff right here. Not the prettiest box, but you get the picture. And in goes our alkene, C3H6. In goes our water. And out comes our diisopropyl ether, which is C3H7O C3H7, and our alcohol, which is C3H. How many hydrogens is that? That's 1, 2, 3, 4, 5, 6, 7. C3H7OH. So now, oftentimes as chemical engineers, we have to remember the fact that not every reaction is going to be 100% pure. And so it's not wrong necessarily to have these as, you know, how we've listed them, our diisopropyl ether here and our isopropanol. It's not wrong, but it would be more accurate if we just called these the ether product and the alcohol product. And again, we call it this way because it's probably not going to be a 100% pure product. 100% pure is crazy. It's not something that happens like very often, if ever. And so we can simplify this down to having an ether product and an alcohol product. So say if we were to make ramifications to this process, trying to improve it a little bit, the first step would be numbering our components. So if we go off to the side here, uh, and let's go, we have 4 components. So 1, 2, 3, 4. Now, it's common practice to have our most volatile component first, our least volatile component last. And so our most volatile component is going to be the alkene, our propene or propylene, however you would want to call it. That's going to be our alkene. The next most volatile is going to be our ether product. And then comes our alcohol. And then our water comes dead last in that list. So now that we have our ordering and whatnot, all our logistics down, we can start looking at the mole fractions for each of these. So just by practice, usually when we have a gaseous component like our propylene here, we use Y for our mole fractions. We use X for our liquid mole fractions. Not a big deal, just how we do the nomenclature for that. So let's go ahead and just try and specify this a little bit, right? So we have a propylene feed here. This is our propylene feed, denoted by Y. And so Y is going to equal some array, some vector here. And propylene came first on our list, our alkene. So that's going to take our number 1 spot in our array. So we are inputting 100% of our alkene. For our water, it's going to be 100% water, pure component water. So we are inputting pure components. However, now, if we look at the output for our ether product and our alcohol product, we have a couple specifications here. We have these specifications for our ether, and we have these specifications for our alcohol. So using that test case, let me just move you over a little bit. That should be good. So let's say the X for our ether, we're saying that we'll see, that doesn't add up to 1. So it's 0.009. Let's see, that's 0.1, 0.1. Yeah, that should be fine. So we're going to have 0.001, 0.9 is going to be our ether. That's going to have the highest concentration. Then we're going to have a 0.09 and a 0.009. And the reason why we're using the 0.001 is because that we're not necessarily going to get rid of all of the ether, although we're going to get rid of most of it. It's not going to be a huge part of the makeup, but of course, chemistry is a little bit nasty in that regard, so we just have to deal with it. And for our alcohol, it looks like we're going to have, again, we're going to have a very low amount of our initial alkene. We are going to have 0.01 ether. I think it was 0.94 alcohol and 0.049 water. Double check, that's 0.05, 0.99 plus point. Yep, that should be good. I'm going to make this a little bit bigger just so it's easier to see. There we go. And so now we have specified the values for the mole fractions per each of these components. One more thing that was specified in our initial problem is we have propylene and water feed flow rates of 195 moles per second. So we can also put that in there. Use a different color to make sure it's a little bit easier to see though. So our propylene is at 100 mole per second, and our water is at 95 mole per second. And with that, we now have this word problem that we are able to solve by finding our unknowns, writing out equations, and doing a mass balance for this entire system to find the outflow rates for the ether product and the alcohol product. So now we're back in co-laboratory, and the first thing that I did here is from our GitHub page, I pulled out a few things that we're going to be using later on. I've also imported NumPy, SciPy, and a couple other things that we're going to be using later on, as well as rewriting out the reactions that are going on within our reactor. So let's start off by we'll define our alkene feed. And if you remember, the rate for our alkene feed was 100 moles per second. So moles per second. And the alkene composition, so alkene comp, we're going to set that as an array. And that's going to be 1, 0, 0, 0. And remember, we're doing that because we have 100% pure, or I guess we're assuming is a better way to put that. We are assuming we have 100% pure our propylene. We have 100% pure propylene for the inflow. So now we could also do our water feed, which is going to be 95 moles per second. 95 moles per second. Ooh. Forget the hashtag. And the water composition looked like 0, 0, 0, and 1. And again, making sure to follow our order for each of our components. Make sure it is the same in the array and everything we do later on. Now the next thing we might want to do here is we can write out the stoichiometry for each of the reactions going on, right? So if we go stoich of reaction 1, and we'll set that equal down to an array. And so in Python, it doesn't necessarily know what reaction we're talking about. It isn't that type of software. But what we could end up doing is represent what is being consumed in a reaction and what is being produced in a reaction as positive and negative magnitudes. So in reaction 1, if we take a look back, we see that we consume 1 mole of propylene, 1 mole of water to produce 1 mole of isopropanol. So remember that number 1 is our propylene. So we're going to have -1 because 1 mole of that is being consumed. We are not consuming any ether, so that's going to be a 0. We are producing 1 mole of our isopropanol, and we are consuming 1 mole of our water. So that's going to be for the first reaction. Now for the second reaction, stoich reaction 1 or 2. Now for this one, we are consuming 2 moles of our isopropanol, 2 moles of our isopropanol to produce 1 mole of diisopropyl ether and 1 mole of water. So we are not doing anything with our propylene. We will be producing 1 mole of diisopropyl ether. We will be consuming 2 moles of our isopropanol, and we will be producing 1 mole of water. So now we have our reaction in terms of the stoichiometric coefficients. Now the next thing we end up doing is we can go ahead and type in the compositions of the ether and alcohol flows. So if we go ether composition, this is going to be another array. And if we look back at our whiteboard, we have, let's get you side by side here. Right? So we have 0.001 for our propylene composition, 0.9 for our ether composition, 0.09 for our alcohol composition, and 0.009 for our water composition. And then we end up doing something similar for our alcohol composition too. P.array. And this one, we again had 0.001 fraction of propylene. And 0.01, 0.94, and 0.049. And now we have a good amount of information here. Now, you might be asking why we have all these arrays that we are determining here. And the reason for that, I didn't mean to split this up. The reason why we want to stay so organized here is because we look here. We have our stoichiometric coefficients here. And we have arrays that align with the values in these arrays here. If we were to multiply the alkene composition by, let's say, the first stoichiometric reaction where we're consuming that propylene, well, then we get how much propylene we are consuming at a certain rate. And thus we are able to get the total moles of alkene that is going into our reaction, and thus we can also calculate how much ether is coming out. What does the ether stream look like? What does the alcohol stream look like in terms of composition and mole fractions? And so it really is just a way of staying organized and making things a little bit easier on us by structuring this out the way it's happening in the reactor almost. So let's move on to the next thing here. So now, a couple other things we should define here is we want to find our ether flow. And for this one, we're just going to make some guess. Let's just say it's 5 moles per second, right? And same thing for our alcohol flow. Alcohol, if I can remember how to spell. Alcohol flow. Just 100. Why not? 100 moles per second. We're just making some guesses here, basically. And we also want to do the extensive reactions for both reaction 1 and reaction 2. How many moles are we going to create? How many moles are we working with? So let's say the extent of reaction 1 is 90 moles. 90 moles. Oh, come on. And then the extent of reaction 2, let's just go 10 moles. And then from here we can go on and we will use our equations to calculate. Well, let me just show you this, right? So we're going to define EQs. We're going to take some vector as an input. And what we're going to do is we're going to, what we don't know right now, what we're really just guessing for is our ether flow, alcohol flow, and the extents of our reactions. So we're guessing those. So we'll unpack our vector into that. So ether flow, alcohol flow, our extent of reaction 1, and our extent of reaction 2. And now what we want to do is use our equations that we know. So first thing we can do is we'll calculate the feed. And the feed is going to be equal to, let's see, or rather, let's go reactants is going to equal our alkene F times our alkene comp plus our water flow times our water composition. And so that's what we're working with. Our products, that's going to be equal to our ether comp, or I guess ether F times our ether comp plus our alcohol flow times our alcohol comp. And let's see, what else are we missing here? Oh, so we also need to determine our, or hold on. We also need to define something. I can't remember I'll give it a name in a bit here. But we should also find out our extensive reaction. So that's going to be our stoic of reaction 1 times our extent of reaction 1 plus our stoichiometric reaction 2 times our extent of reaction 2. I think this might be our feed. Or, so our feed isn't that. This is our reactions. That's what's happening in our reactions, right? Our feed is going to be this here. Remember that we had an intake of our alkene feed and our water feed. So this one's going to be our feed, and our products are going to be, of course, our ether and alcohols. So we're going to return our feed plus our reactions minus our products. And so our reactions are going to give us the amount of moles that we are working with in terms of how much ether and how much alcohol is being produced. Our product is going to be what is flowing out at the other end. And our feed is how much of the initial product, our initial reactant we have for the reactions. So if we take our feed and add the reactions, which will be positive or negative depending on what the stoichiometric coefficients are, we add our reactions and minus our products. Well, if we are following the conservation of mass, the return for this function should be 0. So could put a note here, it should be 0. And that's because we're conserving mass. Everything that we're putting in is either reacting, or everything we're putting in is reacting and then flowing out of the system. So there should be no accumulation. That's basically what we're calculating here. This is accumulation. There should be no accumulation inside of the system. Everything that comes in reacts inside the chamber and goes out. And that's what this return is going to confirm for us. So the last thing we want to do here now is we're going to use our root function, and we're going to use it on the function we just defined, and we're going to we'll put our inputs in the same order that we have these inputs in, right? So let's just do this and let's run it. So our solution converged, and we're interested in this x here. So let's just pull that out here. And there we go. So according to what our root function is displaying here, our flow of the ether isn't 5. It's actually closer to, it's a little bit above 9 moles per second. And same thing with our alcohol flow rate. It's not 100. Instead, it is around 85 moles per second. And the extent of reaction 1 is closer to 100 than it is 90. Our extent of reaction 2 is actually not that far off of a guess. It is 9.19. So using all this information, using our root function, we now see the molar flow rates and the extents of the reactions for reaction 1 and reaction 2 according to our stoichiometric coefficients, our compositions, and all these other things that we have. And what this really displays is our degrees of freedom. We talked about degrees of freedom in the last video, and since we have all this information for us, we have filled the required amount of degrees of freedom, we are now able to figure out all the rest of our unknowns. So that is a more absolute application of degrees of freedom.